Welcome everyone. Wanted to take a look at the calculations for chapter 6. And while this is Newton's third law for the chapter that we're in, it pulls together some from the first and the second as well. So if you see that, your formula sheet or the practice dips back into the previous chapter with Newton's second law, I think it kind of pulls together nicely. So we've got to go back and review Fermat. You might remember that Newton's second law is affectionately referred to as Fermat, where like the first law has inertia, that's kind of like its nickname. And then the third law is generally just like action-reaction, if you wanted to have a reminder, just sort of like a quick-off nickname. So these should look all real familiar, right? For our abbreviations, we've got force, mass, and acceleration. If you're not certain of what these were, I would encourage you to look back on materials from previous units. You should be good also with units, as we've discussed them quite a bit. If we're dealing with force, capital N, in honor of Sir Isaac Newton. Mass, we're primarily sticking with kilograms. I believe all the examples that I give you here are in kilograms, but if it was grams, that'd be fine, but that's our unit for mass. And acceleration, sometimes referred to as the tricky one because it's got the squared. Remember, just meters per second, that'd be velocity, but we're looking at the rate at which that velocity changes. So this would be how many meters per second does something accelerate, or does it change? So before I even get into an example of the calculations, just here's something I want you to think about. There's a difference between acceleration and effect. And there's a difference between the amount of force and the effect. And I know I am not much of an artist here, but this is an example, depending on when you see this, that's been discussed in lecture. And this hot rod here is gonna blow your mind. All right, there's my vroom vroom. Oh, here we go, might as well really doctor it up, right? A little door, and there you are, happily driving. And we're gonna say that you're cruising around in your car. There's a little bug. You keep driving. We'll say this is expressway speeds. Bug hits the windshield. So if the bug hits the windshield, hopefully you're at a spot where you could make like an action-reaction statement of that, or you could use Newton's third law to describe what's taking place. If I say that the bug hits the windshield, or in this example, if I said the bug pushes the windshield to the left, you could have the reaction statement of the car pushes the bug to the right. So if we were to look at that force, remember the other way that I'll often refer to, or something that I'll pin on with Newton's third law, is equal and opposite. So there are really two forces here, right? A force pair. That's, pair is like if we're playing cards and I got a pair of aces, I've got two. So there's force pair. There's going to be two things here, right? The car and the bug. And if we're looking at that force pair, and it's got to be equal and opposite, that means that however much this car hit the bug hit the car. Or whatever that force is, it's got to be equal on both, but in opposite directions. In this case, the bug goes to the left and the car goes to the right. Here's where some kids will get confused. They're like, well, this bug explodes. Dunzo. That's it. Car's fine. That's true. So was the force the same on the car and the bug? Yes, the force was the same. Was the effect the same? No, absolutely not. So why would that be? Think about the mass difference here, and this is where we can kind of sometimes reach back into Newton's second law stuff, and we pull it all together, and it starts to make a little bit more sense, right? Whatever the mass is of this car is very, very big. Whatever the mass is of this bug is very, very small. And if we're saying that the force was the same on both of these objects, large mass with that force, small mass with that force. What's that going to change? Right? The acceleration. And that means that this acceleration on the vehicle wouldn't even really be felt, because that force on that much mass isn't really going to change that acceleration much. That force on that mass, it's going to completely change this acceleration and consequently the effect, destroyed, exploded, fine, moving along. So this may be review, or it may be the first time you heard it again, depending on when you're going through these calculations, but it was something I just wanted to touch on. I also want to go through an example with you because they look kind of confusing. And by kind of confusing, I've given you your organizers, but there's two, because I wanted to make some comparisons here. If we're looking at force pairs, where these forces always occur in pairs and they're equal and opposite, maybe we could make some comparisons. So don't be surprised when you start getting extra numbers. And the reason being is you have to kind of organize one scenario to another scenario, and then we can make those comparisons. So I'll go through this first one with you. Step one, read the problem. All right, so what is the acceleration of a 2,200 kilogram jet compared to a 200 kilogram jet when their rockets generate 500 newtons of thrust? Okay, so I got two jets that are same engine, or at least generating the same amount of thrust. Looks like one's going to be substantially bigger. And this is where, if you're still struggling, or you just like to even kind of double check or make sure you're on the right track. Remember, if we see kilograms, even though this might not come right out and say the mass of the jet is, I know if this is measured in kilograms, that's got to be mass. So I'm just going to make this guy the first one. And I'm going to say, all right, well, there's 2,200 kilograms with that jet. And then now with this jet, the mass is only 200 kilograms. It's a little guy. We're looking for acceleration, all right? So I'm looking for acceleration. That's what I wanted to compare on each of these. And the force is the same. Now, if you were given this much force on this and that much force on that, it might be important to make sure that you lump the correct mass and force together. But we're just saying both these engines generated the same amount of thrust. So I'll say, okay, well then there's 500 newtons and 500 newtons. Now, if you don't have your formulas memorized, that's why I gave you this little handy dandy guy. We're looking for acceleration, and there's only one formula that will work with that. So I've got A equals F over M, or acceleration is force over mass. All right, so here I've got 500. It's important that I match force with force, so 500 was at the top. I'm not just randomly pulling this over because it happened to be on the top of my organizers. You got to make sure that force goes in where force goes and mass goes in where mass goes. Make sure force goes in where force goes and mass goes in where mass goes. Should kind of look like we're setting these up before, and this shouldn't be too new, but it's okay. If we took a look at another example, so I'm going to enter 500 divided by 2,200. And I got that there. I would just stick with going to the hundredths and say, yeah, that 7 should make that go up, and I'd call that 0.23. So here I wound up with 0.23. I was looking for acceleration, so I want to make sure that I've got the correct unit there. Meters per second squared. If you're uncertain, rely on a little cheat sheet here. That's why I'll let you use it. Now I got to do the math over on this side, right? And I'm going to go 500 divided by 200 before we give the big reveal. A little bit of common sense here. Think about labs and discussions and examples we've seen. A lot less mass, same force. Do you expect there to be a greater acceleration or not as much acceleration? Same force, a lot less mass. Let's find out together. Dun, 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 dun. 2.5. So here we've got 2.5 meters per second squared. Substantially more, huh? What was that? 10 plus times more. So if we're looking at that much mass compared to that much mass, indeed, the smaller jet would accelerate faster with that same force. So you kind of have to work through the two problems, but this is mathematically just confirming some of the things that we've discussed in previous lectures. One last example here that I want to go through with you. There are some action reactions, and I'm not telling you that this is how you have to do it, but if I ask you to write an action reaction statement, this is what I would do. I'd just say, okay, well, action equals reaction equals. Write an action reaction statement for a dart that pushes a dartboard to the right. So remember, there's really kind of two parts to this, right? I gotta first figure out, okay, well, what are the objects, or what are we even dealing with here? And in this case, it's a dart and a dartboard. Then I gotta ask myself, well, who's pushing on who and in what direction? And then for my reaction, I can just flip the nouns and change the direction. If I'm losing you with that, let me give you the rest of this example. I'd say the action is dart pushes dartboard to the right. Now I can take my nouns, the dart and the dartboard, whoop, whoop, flip-flop them. Dart board pushes dart to the left. Now, I didn't mathematically give you any force here, but you should be at a spot where you're like, well, yeah, this is an interaction. The force pairs, action reactions, there's got to be two things, and whatever the interaction or whatever the force is has to be equal and opposite. So pretty simplistic here, right? Or correct, right, left, left, right. Those are clearly opposite. If we know the force, or actually I guess even if we don't know the force, it's going to be equal regardless. So work your way through these. If you've got questions, concerns, please don't hesitate to reach out. I would encourage you to have your little formula cheat sheet out as well. And like I said, if you've got questions, let me know. Take care.